W6, stationary and progressive waves. The photograph here is of something called a Chladni plate, which is a large sheet of metal. It's attached in the middle to a vibration generator, which is shaking the whole thing up and down very, very fast. And the white stuff you can see is salt or sugar sprinkled on top. And where the plate is stationary, the salt accumulates. So you can see the white bits. Where it's shaking very, very hard, the salt can't settle. So you get a bare metal patch. So you get these rather lovely shapes as you change the frequency. So, progressive waves, we've already looked at. They're any wave that's travelling away from the source of the disturbance. And it's the energy that's travelling, remember, not the medium. But you've got energy moving away from the point of origin. Stationary waves, on the other hand, are where the wave appears to be standing still. And you can get that with two waves that are travelling through each other. But you need special conditions apply. So you need conditions where you can get a stable pattern. So the question is, how do you achieve that? Well, basically what you need is a fixed space for the waves to interact in to produce this stable interference pattern. And the fixed space has to be the right size to fit in a whole number of half wavelengths. So two key bits there, whole number of half wavelengths. The simplest pattern that will fit into this space is called the fundamental. So for example, on a rope, the simplest pattern, stable pattern you can make is a single loop like this. There we are, a rope. Now, a single loop is actually half a wavelength. If you think about what this rope is doing, the solid line here, that's a peak. A short time later, it will be in this position, forming a trough. But in the picture, you only get one or the other. You don't get both, and you need a peak and a trough to make a whole wave. So we've got a half wavelength here. Now, if you shake the rope harder, the frequency will go up. So the equation is V equals F lambda, so as F increases, lambda decreases. So here's our wave. If you shake it harder still, you get 3 loops. Faster still, and 4 loops, and so on. You can just keep going. And each stationary point is a node. And in the top diagram, a single loop, the different distance between two nodes, is still half a wavelength, lambda over 2. And that continues regardless of how many loops you've got. A single loop, it still is equivalent to half a wavelength. Okay, now if we think about the amplitude of particles along a rope, they vary with their position. So here's a rope with 3 loops on it, and I've got 4 particles marked in grey, which are travelling up at this particular moment in time, and I've got 5 particles marked in orange, which at the same time are travelling downwards. Okay, so all the grey arrows are in antiphase with all the orange arrows. They all have different amplitudes, but all the grey arrows are in phase with each other. All the orange arrows are in phase with each other. They're doing the same thing, the same direction at the same time. But all the grey arrows are in antiphase with all the orange arrows, and obviously that continues further down the rope, in between the nodes. If we think about the phase difference between adjacent loops, so here we've got 4 loops. I've drawn 3 blue points on the wave, and if we think about what they're doing, they are still all going up at the same time. So all those 3 blue arrows have a 0 phase difference. They are in phase with each other. The green arrows I've drawn here, on the other hand, they're doing the complete opposite. They're going down when the blue particles are going up. So they are in antiphase with the blue particles, but in phase with each other. So the phase difference is 0 if the particles are between adjacent nodes. So that's like these two. That particle and that particle are between the same two nodes, here and here. Okay, so any particle between those two nodes are in phase. Or if they're separated by an even number of nodes. So these two blue particles are still in phase with this one because they're separated by 1, 2 nodes, an even number. The phase difference is pi radians, or you could say they're in antiphase if they're separated by an odd number of nodes. So if I pick a particle in this loop, this particle here, and compare it to a particle in this loop, they're separated by 1 node and they're in antiphase. And if I consider this one here, the blue one, and a green one right over here, they're separated by 1, 2, 3 nodes, still an odd number. So they still have a phase difference of pi radians. They're in antiphase. Now, one interesting thing about stationary waves is if they vibrate freely, they don't transfer any energy. If you remember the progressive wave, the energy travels away from the source. But with stationary waves, the energy is trapped in the space. And what you get is a swap, a transfer between elastic potential energy and kinetic energy. And they just keep swapping backwards and forwards. Which is why something like a guitar string keeps vibrating for a long time. Obviously, in the real world, the energy does leak away slowly, in this case turning into sound. But you've got this, say, long transfer between stored energy and kinetic energy in the wire.